Welcome to my lecture series on group theory. Today we are going to discuss one of the most fundamental theorems of group theory, and the name of this theorem is Kls Theorem. Here is a statement of the theorem. It states that every group G is isomorphic to a group of permutations. So to prove this theorem, we see that we in this case are given only with this group G. So first we need to construct a group of permutations, and then we would need to define an isomorphism from the group G to that group of permutations. So let's proceed first to construct that group of permutations. And we know that group of permutations is basically the group of bijective mappings from a set to itself. So we consider the group G be a group, and for each element G from the group G, we define a mapping phi G from G to itself by phi G of any element X of the group is equal to Gx. And now we prove that this mapping is basically a bijective mapping. That is, we need to prove that this is both one-to-one and onto. So to prove that this is one-to-one, consider phi G of X equal to phi G of Y. And using the definition of this mapping, we will have Gx equal to Gy, or this implies that X is equal to Y. So if two elements have the same image, basically those two elements are the same then. That is, the mapping is one-to-one. Now we prove that this mapping is onto. To prove that this mapping is onto, we consider any element Y of the group G. And then we can see that this element Y of the group G is the image of this element of the group, because this is equal to G times G inverse Y. And using the associativity, we know that this is equal to Y. And hence, any element Y of the group G is the image of G inverse Y. And hence the mapping is onto. That is, the mapping phi G is a bijective mapping from G to itself. And now what do? We collect all these mappings in a set, and we name it as phi G. That is, phi G is the collection of all such mappings. And we prove that this is a group. So to prove that this is a group, we consider phi G and phi G dash from this set, and we operate phi G times phi G dash on X. So using the definition, we can write this as phi G times phi G dash of X. And using the definition of this mapping, this can be written as G dash of X. I'm sorry, this is not here. This is G dash of X. Or once again, using the definition of this mapping and using the associativity, this can be written as Gg dash times X. And hence, this can be written as phi G dash of X. That is, phi G times phi G dash is equal to phi G, G dash. And we call it equation 1. Further, we can see that phi E belonging to this group, belonging to this set phi G, is an identity element of this set, because phi E of x is equal to Ex by definition, and this is equal to x. Hence, this element belonging to this set is an identity element. And for each G belonging to the group G, phi G inverse belonging to this set is the inverse of phi G, because we know that phi G inverse of x is equal to phi G inverse of x, or this is phi E of x, and hence phi G inverse of x is equal to phi E. Hence, this is the inverse of this element, and thus phi G is a group, and it is a group of permutations because it is the set of bijective mappings phi G from G to itself, and hence this capital phi of G is a group of permutations. Thus, we have the group G and the group of permutations phi G. So, the only thing that we need to prove is that there exists an isomorphism from G to phi of G. We define a mapping psi from G to phi of G as follows: that for any G belonging to the group G, psi of G is equal to phi of G. Then we prove that this mapping psi is an isomorphism. And for that, we need to prove that this is 1-to-1, this is onto, and number third, that this mapping is operation preserving. So, we proceed as follows. Number 1, to prove that this is onto, we know that if we take any element phi G from this group phi G, then this phi G is the image of G belonging to the group G by definition. And hence, this mapping is onto. To prove that this mapping is 1-to-1, we consider G1 and G2 belonging to the group G and assume that they have the same images under psi. That is, psi of G1 is equal to psi of G2. And hence, by definition of this mapping psi, this would imply that phi G1 is equal to phi G2. Or, we can further write this as phi G1, phi G2 inverse is equal to phi G1, G2 inverse, which is equal to phi E. and hence it further implies that G1 G2 inverse is equal to E, or it means that G1 is equal to G2. That is, if two elements G1 and G2 have the same image under the mapping psi, then basically those two elements are the same, and hence the mapping is 1 to 1. So far we have proved that this mapping psi from the group G to the group of permutation is both onto and 1 to 1. So the last thing, we need to prove that this mapping is operation preserving. So for that we consider, for operation preserving, we consider two elements of the group G, G1 and G2 belonging to the group G, and we take the image of G1, G2. And by definition, we know that this is phi G1, G2. And using equation 1, we can write this as phi G1, phi G2. Or, once again, using the definition, this is psi G1, psi G2. And hence, the mapping is operation preserving. So, we have proved that psi from G to this group of permutation is an isomorphism, and which basically proves our result, that is, every group G is isomorphic to the group of permutations, which is the proof of the Kls theorem. Thank you.